Okay, so welcome back to another video. So here we have a trig slash hyperbolic identity that we would like to prove, and that is to show that sine of g dx is equal to the hyperbolic tangent of x, where g dx is the Gudermannian function. So what's nice is that this function actually relates a hyperbolic angle measure x to a circular angle measure y, as denoted as the Gudermannian of x, where y is equal to gd of x. So to put it in other words, it actually relates the area of a circular sector to the area of a hyperbolic sector. So some stereographic projection. So it was also discovered in the 1760s by Johann Lambert, but actually was given the name the Gudermannian function by Christoph Gudermann in the 1860s. So on the way to how to prove this identity, we're going to evaluate what is the Gudermannian function. So the Gudermannian function is defined as, for all x in the reals, as gd of x is equal to the integral from 0 to x, typically defined in between negative infinity to infinity, of hyperbolic secant of t and then dt. So we'll be using this formula to, of course, evaluate that function itself. Then actually, once we get to that whole evaluation, then we will use that to actually help verify the identity that we want to achieve for. So pretty much that's the outline from here. So there's a bunch of trig identities we will be using along the way as well. So why don't we just jump right in? So hyperbolic secant of t, in other words, I can write that as, so from 0 to x of 1 divided by the hyperbolic cosecant of t. You can just think that similarity to like secant of x is the same thing as 1 over cosine of x to that, but this is the hyperbolic function we're dealing with. So using that definition, we know that hyperbolic cosine of t is equal to e to the t plus e to the negative t divided by 2. So that's another exponential definition for the hyperbolic function of hyperbolic cosine function. And so it's under the denominator, so I'll just flip the reciprocal. So now that's going to be 0 to x of 2 divided by e to the t plus e to the negative t and then dt. So what's nice is that I'll just multiply the e to the t to both the top and bottom. We'll just reduce everything out a little bit easier. And so now we'll have the integral from 0 to x of 2 times e to the t and then divided by e to the power 2t, and then add this with 1, then dt. Nicely, what we can do is, well, to put things a little more simpler, I'll factor out the 2 from outside. And then on the bottom of the denominator, this is a square, so this is e to the t and then divided by quantity e to the t and then square that, and then add this with 1 dt. So from here, as you can see, we can actually perform a nice little u sub. So I'll let u equals e to the t. So du is going to equal et then dt, then substituting this back in. So now that's actually going to give us the new variable in terms of u. So that will give us 2, and then multiply with the integral from now with our new bounds. Don't forget that. So our new bounds are actually going to be from now 1, and then plug in x for here. So that's actually going to be e to the power x, and then we'll have 1 divided by, so u squared, and then add this with 1. And then this antiderivative is well known that this is actually going to be 2 times arctan of u. And then we'll just evaluate this from 1 and then to e to the x. Very straightforward to see that this is arctan of 2 times arctan of x. And then if we plug in 1 for arctan of u, so that's basically just pi over 4, then multiply the 2, subtract that, and so that's going to be minus pi over 2. And so that actually completes the evaluation of our Gudermannian function gd of x over here. So with this, now we can actually get to the real meat of the video and verify this following identity over here. To put things start off, of course, we'll just substitute in what that value is that we just evaluated for. So sine of g dx, we're going to replace the g dx for our answer that we evaluated. So let me start from the very beginning over here. Then we substitute sine of 2 times arctan of e to the x, and then subtract pi over 2. Okay, so how do we proceed from here? So let's actually notice that we can actually use a bit of some trig identities with the difference of angles. So sine of AB for some angles is actually going to equal to the identity sine of A, then multiply with cosine of B. Subtract this with cosine of A, and then multiply with sine of B. So with this, now let's actually put in that substitution for the values over here. So that will actually yield us, so I'll put this equal to for this line over here. So now this is going to be sine of 2 arctan of e to the x. Then we multiply with cosine of pi over 2. Then we subtract, now this is going to be cosine of 2 arctan of e to the x, and then multiply with sine of pi over 2. And this actually reduces the work very nicely because we know that cosine of pi over 2 is actually just going to approach 0, and then sine of pi over 2 is going to approach 1. So this actually just vanishes and we're just left with this to calculate. So with that, let's continue forward from here. So far now is equals, so this left-hand side right here is so far going to be negative cosine of 2 arctan of e to the x, and then there we have it. So how do we approach something like this? For one, we can actually, there's actually another trig identity we'll be using, and that is for cosine, the double angle identity. So cosine of 2x is going to equal to cosine square of x subtract sine square of x. And what's nice is there's a negative, so that'll actually just flip the signs on that out. That's sine square of x minus cosine square of x, and then just put in that the variable for the input arctan of e to the x. So now that's actually going to yield us sine square of arctan of y, or in this case, e to the x. I didn't mean to say y. It's arctan of e to the x, then minus cosine square of arctan of e to the x. Okay, so far so good. That's what we have. So where do we go on from here? So let's actually do a little bit of some substitution. We'll actually suppose that we let y, a variable, equals arctan of e to the x. So if I take the arctan inverse tangent of both sides, so that means tangent of y is going to equal to e to the x. So let's say we actually draw this triangle out so we can actually find our sine and cosine, because that's actually going to be handy to use in order to do this substitution. So here we know that tangent of y, so our angle y is over here. Let me actually draw the triangle a little bit bigger. All right, so here's our tangent y. So we know from that's going to be opposite over adjacent, and that's equal to e to the x. So opposite, we can tell that that's going to be e to the x, and then for the adjacent, that's going to be 1. So what's the hypotenuse length? Well, just apply the Pythagorean theorem, and so over here, we're going to get that this is going to be the square root of e to the 2x, and then add this with 1. Oh, that a little weird, let me fix that up. So with this, now we can actually interpret what our sine of y and cosine of y is going to be, since now basically we make the substitution that y is equal the following over here. So replace that, so we have sine squared y minus cosine squared y. And that's nice that now we can interpret what sine y and cosine y is from the diagram that I just drew out. So from here, we know that sine of y, after putting all this out, is actually going to be e to the power x, and then divided by the square root of e to the 2x plus 1. And then cosine of y is going to equal to 1 divided by the square root of e to the 2x plus 1. Okay, so when we're here, now we can actually perform the necessary substitutions we need. So putting this back into parentheses, replace sine square of y, so sine of y for here. So it's going to be e to the x divided by the square root of e to the 2x plus 1. Then that whole thing quantity squared, then subtract. This is going to be 1 divided by the square root of e to the 2x plus 1. Then quantity square, as we see that the square roots are going to cancel. And so that means I have e to the 2x from the top, then divided by e to the 2x plus 1. Subtract with subtract with 1, and then divided by e to the 2x plus 1 to get a common denominator. So that's going to be 2 e to the power 2x subtract 1 divided by e to the 2x plus 1. And so what's nice is that this is the definition, the exponential definition of hyperbolic tangent. And so that actually completes the proof to say that, let me put the final verdict over here. So therefore, 3 dots, sine of g dx is going to equal to hyperbolic tangent of x from all this calculation over here. So I underline here, and so it leads to, let me actually put this same color over here. And so therefore, the final verdict is that we actually completed the identity proof that we wanted to do of both the trig and the hyperbolic trig identity that we wanted to show, utilizing the Gudermannian function, just like that. So yeah, that's pretty cool if you ask me. Right above me, just the sky. Pray in your